Well, thanks, Matt. And I should probably begin by apologizing for the fact that much of what I'm going to say will be rather sketchy in nature, but I will try to illustrate at least one of the main points with some examples. And what is the main point? The main point, of course, is in the title, and to flesh it out a little bit more, it's the claim that because of the way quantum mechanical interference works, no two parts of reality, by which I mean regions of space-time, subsystems, to the extent we know what they mean, something like that, can be fully independent of each other. And this is true even when, in the ordinary sense, they do not interact at all. So it's, in a sense, like entanglement, but it goes beyond. It's somehow more radical than what we ordinarily call entanglement. So what I'm going to present comes out of a long period of work with several people. Some of the main ones that are most directly connected to what I'm going to say are listed here. In particular, 2 or 3 in the audience here. Joe and Faye, I guess, are the only ones. So let me begin, or the second beginning, by stating what, to my mind, and which I think also to the minds of many people here, but not necessarily to the minds of the majority of physicists, is the main question that we're dealing with in quantum foundations. And that is this question in red: to what kind of reality does the quantum formalism implicitly refer? Many people, and even many, maybe, perhaps even the majority, even here, the majority of the people would say that it's the wave function. However, I would argue that, although I don't want to get into an argument on it, but I would argue, I'm looking especially in your direction now, but I would argue that if it's the wave function, then quantum mechanics is either incomplete or it's wrong. And this is just a summary of the measurement problem. Either the wave function collapses, in which case it's incomplete, or it doesn't, in which case it gives us a wrong image of reality. But there's a more practical reason, if quantum gravity can be called practical, there's a more practical reason why I don't favor formulations of quantum mechanics based on the wave function, and that is because, arguably, quantum gravity needs this notion of history, which in the case of gravity would be the notion of space-time. Of all the known formulations of quantum theories, the only one that seems adequate, if there is one that seems adequate for quantum gravity, is a histories formulation, which is a kind of general term to cover path integral ways of formulating the dynamics. And that would be a long discussion to say why in great detail, but let me add one fact, which is in the case of causal sets, which are fundamentally, which some of you will know about, which is, of course, the program for quantum gravity that I'm involved in. In that case, they're fundamentally discrete, and when things are fundamentally discrete, including temporally discrete, the notion of Hamiltonian makes little sense. And, of course, canonical quantization is based on the Hamiltonian, and the Schrödinger equation also is based on the quantum analog operator of the classical Hamiltonian. So that's one of the arguments why Hamiltonian formulations or Schrödinger-like equation formulations are not appropriate for quantum gravity. Another, for those who know what it refers to, has to do with the so-called frozen formalism, or what's also called the problem of time, the fact that time, in a certain sense, completely gets lost when you try to work with the Schrödinger equation. Instead of having partial t, you get 0. It's the so-called Hamiltonian constraint. For those who are not interested, especially in quantum gravity, I would offer another motivation for thinking in terms of histories, in that it helps you get out of a rut that quantum foundations thinking might be in, which I'm calling the psi rut. In other words, to focus every question on the wave function. is the wave function, does it collapse, does it not collapse, is it ontic, is it epistemic, there's a few other questions like that, which I can't think of right now. But it always helps to have another way of looking at things, and some of these questions may ultimately turn out to be pseudo-questions, hopefully, if you look at it the other way. And in any case, I think it's helpful to have a wider perspective. And that's another argument for thinking in terms of history's formulations, which very rarely is done in the case of quantum foundational work. So, for the rest of this talk, let's suppose, if you don't believe it, suspend your disbelief and suppose that reality is more like a history than it is like a wave function. So, in that case, maybe I should also specify what I mean by history. It may not be clear to everyone. When people talk of path integral, they say sum over histories. I'm using the word history in that sense. It's the thing that gets summed over in the path integral. So if you were considering a world that consisted only of a single particle, moving through a Galilean space-time, so it's very minimalist, rudimentary kind of world, if that was your whole world, a history in that world would be just a single world, space-time world line, that is a single trajectory of the particle. So that's what I mean by history. It's whatever, from a classical point of view, would have been a complete description of the reality in respect of the given theory. So to take one other example, which would be pure gravity, with a dynamics, just say pure gravity, say classical general relativity. In that case, a history would be a space-time that is a manifold together with a diffeomorphism equivalence class of Lorentzian metrics on that manifold, what's often called a four geometry. If you were doing pure electromagnetism, that is just Maxwell's equations, a history would just be some sort of Minkowski space together with some particular tensor field, antisymmetric tensor field living on the space, and the dynamics would be given by a couple of differential equations for that tensor field, namely Maxwell's equation. So is the concept of history, I hope, clear? No?
So wave function is not a history?
If your idea of reality was a wave function, then if you wanted to do a path integral of wave functions, then a wave function would be an appropriate kind of history. But a wave function is not a history from my point of view, because I'm supposing that reality is more like the kind of histories. When I say history, I mean the kind of histories that occur in classical theories and that enter in quantum mechanics as the argument of the path integral, the argument of the classical action. So this is what I mean by a history.
And reality is just one classical history?
Classically, reality is one classical history, but a lot of this talk will be about what can reality be in the quantum world.
In our world?
In our world.
All this history should be classical, and you think the reality should be a history. So we are...
No, sorry. I said that if we were living in a classical world, then reality would be represented by a single history. But we're not living in a quantum world, in a classical world, and in the real world, reality will be represented by some sort of combination of histories, most generally by, as I'll mention briefly, a polynomial in the histories. But in the very special case of a particular formulation that we call the multiplicative scheme, which I'll introduce in a moment, reality will be represented by a set of histories. So you may think of it, if you like, as many worlds, but the many worlds are not meant to be macroscopically distinct. So anyway, the answer is that reality will be represented by a set of histories, set of classical histories, not a single classical history.
Not as like a history.
Well, like a history. A set of histories is kind of like a history, much more than a wave function is. I said like, more like, yeah. More like a classical history than it is like a wave function. So if reality resembles another sort of fuzzy word here, weasel word. If it resembles a history, then what kind of dynamics is appropriate to it? Sort of by tautology, only the path integral seems like a suitable kind of dynamics for a history. I won't belabor that point, but I will belabor the following point, that if we work with a path integral, we never need to refer to wave functions or the Born rule or anything. We can compute the probabilities of instrument events or laboratory outcomes entirely from the path integral, without appeal to the Schrödinger equation at all. Now, I won't flesh out that claim here for lack of time, but it's almost a triviality when you go into the detail. This ABL formula that we saw the other day goes at least 80% of the way to explaining why that's true. You just write the formula in terms of sum over histories, and you'll see that what I'm saying is true. If you're very careful, you'll see that what I'm saying is not true, because of it only, I think, in a small way, which is that to get the path integral started, one needs some initial set of amplitudes. And unless you want to go back to the very beginning of the universe and cosmological boundary conditions, in practice, we usually introduce those initial amplitudes by an initial wave function. So a wave function does enter usually, but just to get things started. It's roughly, if you like, the analog of a summary of a preparation, if you were thinking in that language. But more generally, in the path integral framework, a wave function serves as a kind of partial summary of the past that gives you whatever information you need to get started on doing the path integral for the future. But once you've got that starting point, you never need to refer to the wave function at all. And as I would argue, or let's say hope, once you use the real starting point, which is cosmological, you never need ever to refer to a wave function. But this point, anyway, is an important one. That if all your aim is to produce probabilities of laboratory outcomes, you can do it all with the path integral. However, was there a question? Okay.
And the wave function, that is the starting point.
Yes. Right, exactly. But, so in other words, if we limited ourselves to instrument events, then the path integral would yield some sort of probability measure on the instrument events. Because when I say this, I'm presupposing a whole bunch of technical results which people have not fully proven, involving decoherence of instrument events and so on. But if we function naively and don't try and model the whole instrument, then one can see that this is true in a much simpler way. However, this is only for macroscopic or for instrument events that we get a probability measure. What the path integral yields more generally is a kind of generalized probability measure, which is not a probability measure because it violates additivity, the Kolmogorov sum rule, and therefore it cannot be interpreted as a probability, and it cannot be, essentially because it cannot be consistently viewed as a frequency in some hypothetical or real ensemble. So the question becomes, but the only handle we have, if we start from the path integral on microscopic reality, is this measure this quantum measure that I'm talking about. But I will not have not and will not define it exactly, but it's just roughly something like the squares of all the amplitudes that go into the given event whose measure you're trying to compute. When I say event, so that's a crucial concept here. An event E is a set of histories. Said another way, it's a question about the world. So a question might be, in this diffraction experiment, does the particle go through the left slit? Another question is, does it go through the right slit? Another question, I don't care which slit it went through, but did it arrive at this point on the screen? All of those are questions you could ask about the world, and they correspond, each of them, to sets of histories, right? The question, does it go through the left slit, corresponds to the set of all trajectories that go through the left slit, and so on. The question, did it arrive at this point on the screen, corresponds to the set of all trajectories that do arrive on this point on the screen. So here I'm using a language that's standard in stochastic processes and probability theory, where history The space of all histories is called the sample space, and an event is a measurable subset of the sample space. So, but it's nicer physically to think of it as a question about the world. Now, if we were doing classical probability theory or classical physics, but in a stochastic setting, like Brownian motion, then an event has a probability, and there's no interference here to worry about. So every event has a probability, and it's given by this so-called probability measure, which is usually, or quite often, represented as mu. So mu of e would be just the probability of that event. The path integral also gives us such a measure that I referred to before, and I said I didn't define it exactly, but it's roughly the squared amplitude of all the histories that go into contributing to that event. But it can't be interpreted as a probability because of interference, for the reason I said. So what can we learn from it? So I think there's a kind of minimal assumption that we can make, and if we drop this, I don't know what we can do with this path integral. And this is just a direct generalization from classical probability theory, which is that if an event has measure 0, then it does not happen, or it cannot happen. The technical term is it almost surely will not happen. And you can make of that what you will. But let's say that it cannot happen. So if we hold on to that one principle, it already gives us quite a lot of information about the microscopic world, so much so as it's going to force us to this inseparability, this conclusion about inseparability. That was the title of my talk. So let's postulate this in general, and I'll give it a name, the Preclusion Principle. So an event or a set of histories whose measure is 0, I will say is precluded, and we assume that it cannot happen in any possible reality, any dynamically possible reality. There would be conceivable realities in which it does happen, but they would almost surely not occur in nature. Now, if you take this point of view, so this is not a slight detour, but this is a slight retreat from the full generality, the degree of generality in which I've been talking up till now. And it will represent the framework for most of what I'm going to say after this. But I want to emphasize before I introduce it that this inseparability is more general than this particular dynamical scheme, which we call the multiplicative scheme. And I hope that'll be clear when I show the examples. So how do we describe a reality? So classically, I said that reality was given by a single history. There's a dual way of saying that, which if you were doing classical physics would be kind of redundant and perverse if you tried to do that. Perhaps, maybe not. But instead of saying which is the history that represents the reality, you say which events happen in that same reality represented by the history. Of course, an event happens if an event, remember, is a set of histories. So in a classical world, an event happens if and only if the true history actually lies in that set. So, the particle goes through the left slit happens if and only if the true history is one that goes through the left slit, and so on. If you were to tell for every event whether or not it happened or it does not happen in the given world, then you would, of course, narrow down what was the actual history if we were doing classical physics. So let's adopt that description and say that we will describe reality more generally by telling which events happen and which don't. And I'll introduce a notation for that, which we call the CoEvent, phi, that tells you whether or not. So phi is a description of a possible world, and it tells you whether or not every event happens. So for every event, if phi of e equals 1, it means that that event happens in that world, and if it's 0, then it means that that event does not happen. And as I said, we dub this a CoEvent because in an obvious way it's dual to the events. It's a map from the event space to actually true-false, or Z2, if you like that. What we don't assume, of course, is that the answers that are given, thinking of the event as a question, the co-event is the set of answers to those questions. And what we do not assume is that the answers given by any particular co-event answer to a single history. In other words, they're not produced by specifying a single history. And in fact, they're not consistent with any single history in general. Now, what, in this language, what does preclusion say, the principle of preclusion? It says that, remember it said that an event whose measure was 0 does not happen or cannot happen. So in formulas that says if the measure of an event is 0, then phi of E is 0, saying that that event does not happen. This co-event denies that event, if you like that word. Now, more generally, well, in general, at least if we assume a finite number of histories for simplicity, one can express any co-event as a polynomial in histories. I won't explain that. It's a sort of not a deep fact, but it's a little bit complicated to explain, and I won't need it as such, because we won't be working with arbitrary co-events in a moment. But in general, an arbitrary co-event can be represented as a polynomial in histories. When I say a polynomial, I mean a polynomial in indeterminates which square to 1 and with coefficients in Z2. In other words, we're dealing with the Boolean algebra. So it's, anyway, the important thing is that this notion of the support of the history is the set of histories that enter into this polynomial. Each history gives what you might call an indeterminate in the polynomial. The smaller the support, the more classical, in some sense, is the co-event. In the special case of a classical world, which is given by a single history, the polynomial is just that history, and the support is just that history. Now that may sound, and probably does sound, a little confusing, so let me immediately jump to the special case that I'll be talking about in the rest, when I do talk about a particular dynamical scheme, what we call the multiplicative scheme. In general, the polynomial has a support, it's a set of histories, but just knowing that set of histories doesn't tell you fully what the co-event is. In the case of the multiplicative scheme, it does. The support fully determines the co-event, and it determines it by a simple rule, which is which is illustrated here, and which is an obvious generalization of the rule I gave for the classical world, which was where the support was a single history. The rule is that an event happens if and only if it includes the support. Remember, and the support is just a set of histories. So remember we said in the classical world an event happens if and only if it contains as an element the actual history. In this case, we're saying it should contain all the histories that go into the support. So here's a picture to illustrate this. I don't know how well the colors come out. They seem pretty good. So this F, which is red, is meant to be the support of some co-event. And then here I've illustrated 3 possible events, sets of history. This is a subset of the history space. 3 possible events, which I've called A in blue, B in green, and C in magenta, I guess. Which of those happen if reality is represented by this co-event with support F? Well, A happens because it contains F. C does not happen because it's disjoint from F, in fact. And B, although it overlaps F, doesn't contain it, so it also does not happen. So that's the rule. And the only other rule that we make, I mean, this alone wouldn't suffice, because it wouldn't give us back in a classical setting. It wouldn't, if there was no interference, it still wouldn't tell us that reality is represented by a single history. Presumably, we want to recover that when there's no interference, so we dovetail nicely with classical physics. And to do that, one can introduce the second principle. The first principle, remember, was preclusion, that events of measure 0 do not happen. So therefore, if A were a measure 0, F would not be a valid co-event, because it would be contained within a set of measure 0, and therefore say that that event does happen. So that was the first principle. The second principle, supplementing it, is this principle of minimality, which is that the support of the co-event should be as small as possible, consistent with the first requirement of preclusion. So this F would be too small if A was precluded, but it wouldn't be too small if B was precluded, because it's not contained within B. Okay. Now, if the pattern of preclusion, now with that rule, and that's a dynamical scheme, or the minimalist scheme that I'll be working with. If that rule is adopted, then we do recover classical reality. If the pattern of preclusions is classical, we recover classical reality in the sense that it becomes a theorem that the support of the CoEvent will shrink down to be a single history. I won't prove the theorem, but let me say in words anyway what I mean by the pattern of preclusions is classical. You can, in thinking of physical situations in which this would be the case, you can think of two kinds of situations. These are classical deterministic physics, but although of course it's deterministic, the initial conditions are not fixed, so it doesn't give you a single history as reality. It gives you a set of possible realities. That's one. The other one would be a classical, random, but not quantum mechanical situation like Brownian motion. So you have a classical probability measure. Both of those cases are examples of where the pattern of preclusions is classical. And what the more general criterion for a pattern of preclusions, for the preclusions to make a classical pattern, is, I think it can be said this way, that any event, that is any set of histories, which is covered by events of measure zero, itself has measure zero. So then there's a theorem that you can prove that if this is the case, then reality will be represented by a single history. However, if there's interference, then in general, then of course this rule won't be satisfied. In fact, most of the quantum paradoxes that involve logical contradictions as opposed to probabilistic ones, so starting with the Hoch-Specker one and going on to the GHZ and going to Hardy's paradox, those paradoxes all come from the fact that the whole of the history space, or some important subset of it, is completely covered by sets of measure zero, events of measure zero, and yet it itself does not have measure zero and can happen. So, as I say, Hoch-Specker illustrates this, and the three-slit diffraction Gedanken experiment, but it's not really a Gedanken experiment because it's actually been done, so it's a real experiment. And it also illustrates it in a simpler way. So let me go to that illustration. Let me mention also that it's what Lev calls the three-box experiment is just mathematically isomorphic to what I'm calling the three-slit experiment. And I could represent it in terms of interferometry, and then it would look identical to maybe one of the pictures you had, although I'm not sure you had exactly that picture in your talk. So, so here's what I mean by the three-slit experiment. So there's a source, it emits a particle. That particle can go through any one of, not two slits in this case, but three slits. And having done so, it can go off in various directions. And for simplicity, we can limit it to just a finite set of directions. And then to further simplify, we can ignore all of those. I mean, there would be, how many would there be? I guess two other, in general, ending points for it. We can ignore two out of the three and just limit ourselves to this, which I've called D. D is supposed to suggest detector, although it's important to say that I'm not putting a detector here necessarily, but it's a place where you might put a detector and look for the particle. So now with that limitation, there's only three histories that we have to consider. So each one of these trajectories is a history. This history represents the particle going through the left slit and ending up at location D. This history is the same with the center, and this history is the same with the right slit. So I've represented A, B, and C as the event that A is the particle going through the left slit, B is it goes through the middle slit, C is the event that it goes through the right slit, and therefore this event that it ends up at D, having gone through slit A, I would represent as AD, meaning A and D. Okay, or you could just read it as a description of that trajectory. So why is it that we cannot represent? Why are the amplitudes visible here? So I've tried to set things up in such a way that the left history, AD, has an amplitude of +1, as does the right history, whereas the central history, which would be BD, has an amplitude of -1. So in this case, the history space, we've carved it down to only 3 histories, but there are preclusions. So the event AD the event AD or BD, that's consisting of the first 2 trajectories, that has measure 0 because there's destructive interference here. So in practice, what it means is if you were to block off the right slit, then you would never get any readings, any what's the word I'm looking for? When the detector registers a particle. Clicks, okay. Clicks, let's call them clicks. But there's a photomultiplier. Okay, let's call it a click. Yeah, so we'd never get any clicks at D. And in the same way, the event B or C with D also is precluded. It has measure 0. And we'd never get any clicks if we blocked off the left slit. So, however, if we leave all 3 slits open, of course, the event D is not precluded, and we would get clicks. So remember, now, when I say that an event is precluded, I don't mean something like if an external agent comes and measures it, they won't find it. I'm not even sure how we would set up measurements for some of these events. This is meant to be just a statement about the real world, that event doesn't happen. So the event AD plus BD, in other words, it's the statement that the particle arrives at D having gone through one of the first 2 slits. That event is precluded. And by the same token, the sort of 2 plus 3 event is also precluded. So if we were to identify reality with a single classical history, we'd get a contradiction. Because if it was this one, then the event AD plus BD would have happened. If it was, say, the right one, then the second event, precluded event, BD plus CD would have happened. And if it was the middle history, it would be even worse. Both of them would have happened. And neither one is supposed to happen. So what is this? So the solution is to choose the support, that is the set of histories representing reality, as small as possible, consistent with these destructive interference. And it's easy to see that the answer in this case is that the support is the event AD plus the event CD, by which I just mean the set consisting of the history AD and CD. So like box 1 and box 3 in the box language. That's the unique, yeah?
So we should expect no trace in B.
Well, let's not get into it. I mean, I'm not trying to deny that if you do a weak measurement, you'll get -1 at B, but that's a different experiment. That's a different experimental set.
What operational meaning of this picture?
I tried to say before that it has no direct operational meaning. The whole point here is to talk about reality in a way that doesn't require everything to be immediately traced back to an operational meaning. If you adopt that point of view, then I think we can just stick with Copenhagen interpretation. We don't need anything. And we'll be stuck when we come to quantum gravity. We'll never get anywhere because there's no observers in the early universe. There's no laboratories. There's no... when I say we'll never get anywhere, I mean those of us interested in quantum gravity will never get anywhere.
Nobody.
There's no observers inside a black hole to tell you what happens. So we're faced with a more indirect question, right? It's not that every single statement of which event happens and doesn't happen has a direct operational meaning. Some of them must, of course, otherwise you haven't made contact with reality. And as I said before, all the ordinary laboratory ones do, yeah.
But I guess the point is not that you would make a measurement and see what happens, but suppose you add a perturbation.
Yes.
You add another quantum system next to it.
Yes.
And then you will see that in that case, this middle event will have a history associated with it.
Quite likely,
no matter
yes.
how small that perturbation is.
Well, it's a little trickier.
This image is not stable under small perturbations.
Well, that's an important, let me rephrase that point. So preclusion is not stable under small perturbations. Right? And this, because preclusion as we're using it now says that the measure has to be exactly zero. So it's an important question, how do we treat approximate preclusion? And that's also related to the issue of how do we get probability rules out in the general situation. I'm pushing that aside for now and just dealing with these simple logical situations. It opens up a whole discussion, which maybe we can have in the question period or later, which is how does one deal with approximate preclusion? Is it realistic that there are exact preclusions in nature? And I think it is, and it's related to discreteness, but that's another whole story. So I'm trying to represent a sort of bare bones situation in which we don't, in which we have to deal only with perfect preclusion. Okay, so in this case, the unique solution is the unique that is the unique CoEvent is this one that I've written here. But this is misleading. It's not that a unique one is picked out, and by any means, in a general situation, a whole range of CoEvents will be consistent with the quantum measure that you started with, that is the path integral that you started with. So I don't want to say more in detail about this. It was just partly to set the stage for what I want to concentrate on. But let me briefly describe what I think are some of the successes of this kind of approach. So the first one is that if we limit that to a certain extent it solves the measurement problem. More precisely, although not totally precisely, what I mean by this is that if we limit ourselves to records, we solve the measurement problem. To the extent that we can reduce the measurement problem. So I should say, how does the measurement problem appear in this framework? It really just reduces to the statement that macroscopic events behave classically. That if we limit ourselves to just asking questions about the macro world, we never get an answer like we did for the three-slit experiment, where this outcome didn't happen, this outcome didn't happen, but the event which represents this outcome or this outcome did happen. That's the kind of thing that was going on in three slits. That would be a disaster for the macroscopic world. So one wants to prove that if we limit ourselves to coarse-grained histories, so to speak, macroscopic events, one and only one of these coarse-grained histories will happen. And one can actually prove this if these coarse-graining is done by records. In other words, if you ask yourself at sort of the end of time, the kind of end of time maybe that Adrian was talking about, if you ask yourself, if you limit yourself to those events, asking which record happens, you will always find one and only one record will happen. So that, I think, is a significant step towards resolving the measurement problem. Furthermore, in toy models, we can answer certain other questions that have sort of bedeviled quantum foundations. A very old, I think one of the oldest questions might be, consider the decay of a spinless particle. And then you put detectors, or in those days it was a cloud chamber. So you see, although the spinless particle is completely rotationally symmetric, the actual track of the decaying particle picks a certain direction. It's certainly not rotationally symmetric. So how did this symmetric wave function manage to translate itself into an anisotropic kind of macroscopic reality? In this case, there's nothing mysterious about it, because that one wave function is not the description of the system. It's the CoEvents, and there are actually many what you would call a spinless particle before it decays is actually, and then you study the process of decay. That whole sequence of events, that whole process will have many CoEvents to describe it, and none of them, or a very small fraction of them, will be actually symmetric. Each one will have its own direction. So, I mean, one can see this in simple toy models, as I said. You see exactly this happening. The simplest toy model in which you can see this happening is what I call sometimes three-site hopper. It's a particle hopping on a lattice of three elements. I'll I'll talk about the two-side hopper in a little bit. Also, if there's no wave function, where is the information about quantities that we normally associate with the wave function, like energy and momentum and so on, if we're in a position representation? Well, it can and it does reside in the particle's trajectory, or more properly in the set of trajectories that represent the support of the coevent. Moreover, in reasoning about which coevents, in reasoning about which events happen and which don't with respect to a particular coevent, it's possible to use most of the familiar logical rules, which we could just think as algorithmic rules for reasoning about possible worlds. Most of these rules, like so-called modus ponens, and that relate the happening or the non-happening of events to each other, almost all those rules go through, so that's helpful in analysis. So all this is very good, but there is at least one snag, and that's the one that I want to concentrate on, which is this, what I'll call radical inseparability. So now, where does this come from? So remember that our starting point, by assumption, was the path integral. But, of course, the amplitudes, for those who are familiar with path integrals, which I think almost everyone is, and I gave an example in the case of the three-slit experiment, basically of a simple path integral calculation. For those who are familiar with path integrals, you know immediately that the amplitudes are global. They pertain to the whole history. There's not an amplitude for the part of the history, or if there is, which there is sometimes, you need to multiply it by the amplitudes of the other parts in order to get the amplitude for the whole history. And it's that global amplitude which enters into the into this measure mu, this generalized measure. Or if you're doing transition amplitudes from one state to another, as is more traditional, it's that global amplitude that enters into the transition amplitude. So the amplitudes are global, and therefore global preclusions, that is, cases of total destructive interference, global preclusions can arise even when there are no local preclusions. And that means that the global description of reality cannot be just reduced to local descriptions. So that's just saying the situation in general. Let me now try and illustrate that with a pair of beam splitters, or starting with just a single beam splitter. Now, what do I mean by a beam splitter? So here's, unfortunately, I don't think this, well, I can get most of the picture on, so I'll have to go back and forth. I tried to draw this insofar as space permitted here, so at least those closer may be able to see the same diagram when it's not on the screen. So what do I mean by a beam splitter? Well, okay, so for a certain fraction of you, I know beam splitters are the sort of the bread and butter of daily life, but not for everyone. So let me just define what I mean by a beam splitter. So it's a kind of mirror like this. A particle is, say a photon is coming in, and it may either reflect off or it may go through. So just this setup as a beam splitter. It does so with, thinking of it as just a point particle with no internal structure, say a polarized photon with a fixed polarization. It goes through with certain amplitudes, and what makes it a beam splitter is, I mean, what's required for unitarity of a beam splitter is that the relative phases between the trajectory that goes through and the particle that bounces off is I versus 1. At least that's one consistent choice. Up to phase choices of phase conventions, that's the only possible choice. So here I've just made an interferometer out of a couple of beam splitters and a couple of fixed mirrors here and here that just reflect. So here comes a particle, a source, maybe a laser, who knows. Something has produced this particle, single photon source, for example. And then it has, what are the possible histories in this case? It can go through here on the upper left, bounce off the mirror, and then reach the second beam splitter where it can again go through. Or it could go through here, come to the second beam splitter and reflect, or it could bounce off, reflect at the first beam splitter. So in all, there are 4 possible histories here. You either arrive at this sort of horizontal port via the upper beam or the lower beam, or you arrive at the sort of vertical port here via the upper beam or the lower beam. So those, we can now work out the amplitudes for these 4 histories using the rules that are given here below. So let's take the one I've called here A, which is going through the upper beam, then reflecting, and then coming out the horizontal part. In fact, I'm not going to worry about the particles coming, the histories that come out of the lower part, because we don't need them to illustrate the point that I'm making. So we'll only really consider 2 histories, this one given here by A, and this one here given here by B. So if you follow the rules, we can do it quickly. We can get the amplitudes for these, which I've shown here. I, relative amplitudes, I for the first one and 1 for the second one. Here, if, for example, you go through here, you pick up no phase, you bounce off. Here you bounce off again, you pick up a phase I, so that this trajectory A has phase I. If you look at trajectory B, it picks up it picks up the same I, but I've introduced a kind of phase delay or phase shifter here, which gives it an extra minus I, so it ends up with 1. Okay. So the main thing is that, and of course I've neglected all the phases for propagation, but I've set it up so that they're same for all the particles. So the important thing, I mean, this detail, that kind of detail is not important. The important thing is that I've given 1 a phase of I and 1 a phase of 1. So now, suppose there was nothing in the world but this beam splitter and this photon coming from who knows where, which is not in the world, let's say. Then the only events we have are A or B, or the other 2 which I've neglected. Obviously, neither of these is precluded because each one has an amplitude. One has an amplitude I, one has an amplitude 1. There's no destructive interference between them, so there's no preclusions at all. So classical reality would be, in this case, quantum reality is given by the multiplicative scheme. In that case would be, well, A is one possible reality, B is one possible reality. In other words, the quantum reality would be classical in that simple case. However, now suppose we had somewhere else in the world, maybe a space-like separated, maybe time-like, I don't know, but in such a way that there's no interaction whatsoever between the 2. Suppose we had another setup exactly like this. Well, the rules for combining, the familiar path integral rules for combining amplitudes is that for independent systems, the amplitudes multiply. So now we have sort of 16 possible histories, but I'm concentrating on only 2 each, so we have 4 possible histories. One is AA, which means history A happens in the first and also in the second. I mean, it's the joint history, which is A in the first and A in the second, or also BB or AB or BA. Those are the 4 that we're looking at. But now there's a preclusion because AA, well, remember the amplitude of A was I, so its amplitude is -1. BB, its amplitude, that was 1 squared, so that's +1. So those 2 together make 0. So the event AA or BB, this event consisting of the set containing both of them and nothing else, that event is precluded when 2 interferometers are present. Now, now this is independent of any particular scheme. It's just a fact about the path integral, and it's the root of all this inseparability that I'm talking about. There are preclusions in joint systems that cannot be traced to any preclusions in the individual systems. What this implies in the multiplicative scheme, then, is that neither AA nor BB can happen, but AB can happen still, and BA can happen. So there are 2 possible classical coevents, but there's a preclusion that sets up a kind of, it's reminiscent of an EPR correlation. In other words, this is one possible coevent, AB. It's just a support on a single history, which is really 2 histories, one for each wing of the experiment. But it says that if A happens on the left, then B must happen on the right. Or if B happens on the left, then A must happen on the right. It cannot be that A happens on the left and B happens on the right. But this had nothing to do with entanglement, because I had 2 completely independent subsystems. in this particular case, it doesn't put any further restriction on what can happen on the left alone or what can happen on the right alone. But in general, it gets worse. So if you would do this 3-slit experiment I showed before and put 2 of those, you would find that the possible coevents, even in the single experiment, change. And this is potentially disastrous. There's a couple of other examples I wanted to go through. I don't know if I really have time to do all of them. Maybe I'll just rush through them at the cost of not being very comprehensible. So the next example that illustrates, but I mean especially for this conference I should do it because it illustrates what you might call retrocausality showing up. This is the Hardy paradox. So a picture so again there's a problem with the diagram not being, I was originally going to use the blackboard, but it turned out that you can't see the blackboard at the same time as the screen. So here is this sort of schematic of this setup for the Hardy experiment. You have a source emitting not a perfectly entangled pair in this case, but a pair with the following set of amplitudes. So this plus represents, say, the spin in the z direction. So plus, minus, and minus plus all occur with equal amplitude, but minus is not there. So that's the starting amplitudes that go into the path integral. And then you have a Stern-Gerlach oriented in the z direction here and also in the z direction here. And then the particle emerges in one of these 2 beams, and then I've sort of indicated something that could be spelled out in more detail, but it goes to a recombiner, which reconstitutes the beam as it was before it entered the Stern-Gerlach, and then it goes through a second Stern-Gerlach oriented in the x direction. And in the other wing of the experiment, the exact same setup is there. So what are the histories in this case? Well, here's one history. So it starts, I'm showing half the history. It starts here, ends up in the upper beam, and then ends up, say, in the lower beam on the right. And on the left, it starts here, say, comes out in the lower beam, goes through the recombiner, and ends up in the lower beam. So that's one of the possible histories. In general, there's 2 beams here, 2 beams here, 2 beams here, and 2 beams here. So it's 2 to the 4th, or 16 possible histories. Now, let's look at some interesting events about... And another thing that's not sort of directly represented in this, but that's important, is that these Z beams, I mean, the events corresponding to how you come out of the Z analyzers happen in time earlier than the corresponding X events. So there's a past-future kind of relationship here. So it turns out that there's a lot of preclusions here. I won't list any of them. You can, I mean, they're well known in some sense. But anyway, I don't have time to list the preclusions. But there's a lot of preclusions. There's a lot of set mutually destructive interference, interfering event. There's a lot of events whose net amplitude turns out to be 0 from this destructive interference. And it turns out there's so many that if you were to assume classical world represented by a single history, that the event DD would be impossible. DD meant, I forgot to label this, sorry. So plus minus refers to the 2 beams that come in Z, and UD, up and down, refers to the beams coming out of X. So what it means is that you'd never have an event in which the particle emerged in the lower beam on the left and also in the lower beam on the right. And yet, of course, that can happen. So it's just like the 3-slit experiment, where, well, it's a little different. It's a little worse, in fact, than the 3-slit experiment, but it's the same general thing. So that is, events of measure 0 rule out a classical behavior. In this case, not totally, but if you want the outcome DD. So I have to stop, but tell you what the result is of the analysis in the multiplicative scheme. That you have a total of 6 possible coevents, these coevents that satisfy the minimality and the preclusion requirement. In one of them, the final outcome is UD emerging in the upper beam and the lower beam, left and right. The other one is the reflection, lower beam on the left, upper beam on the right. And one of them, a third one, has lower both, which is the thing that has to happen quantum mechanically. Couldn't happen if we limited ourselves to a classical CoEvent, classical type of reality. Then there are 3 more CoEvents, all of which are classical, and in all of those, they're given by single history, and the event and the particles emerge in the upper beam on both sides. Furthermore, each of the non-classical CoEvents that I talked about, the first 3, they're made up of precisely 2 histories, just like in the 3-slit situation. However, suppose we now take this and we just turn off or we remove one of these X analyzers, one of these downstream analyzers. Then the CoEvents that relate only to the earlier time, which is this ZZ, they will change. If this had been there, and if what was going to happen was the DD event emerging in the lower beam, the CoEvent here would have consisted of 2 possible, support would have been 2 histories. But if we remove this, that CoEvent is just not there. So it's as if the particle at the first stage had something, premonition, if you like, of whether this analyzer was going to be turned on or removed. Or if you like, it's a failure of free will for for whatever is controlling this analyzer. So I had another example, which was the 2-site hopper. Here's a picture, a very brief picture of it. It's just a lattice consisting of 2 sites. The particle hops back and forth between the 2 sites at discrete moments of time. The amplitudes are the same familiar I and 1. I for hopping and 1 for not hopping at that moment of time. So that's the description of it. At discrete times, it hops between x equals 0 and x equals 1 with an amplitude I to hop and 1 to stay put. The difficulty that happens in this case, in this case there aren't many systems, but there's the same kind of, it's sort of, what's the word? It's temporally, what's the word for bones that are articulated? It's temporally articulated. So things that happen later, those are different parts of the history, and they can influence, in a certain sense, what happens earlier. What you find is if you run this for a certain time, and if that time is long enough, it has a severe influence on the CoEvents that are valid for the earlier time. And it's so severe that no non-trivial earlier event can happen. Well, I won't, because I'm really out of time, I can't expand that statement too much. Let me finish by saying, asking whether there are alternatives to this kind of radical inseparability, and do we need them? So on one hand, I think it's a kind of, if you're just a philosopher and not a physicist, you might be very satisfied with it. It's very holistic in nature. You might use the word dialectical. But obviously it could unbearably complicate practical calculations. On the other hand, it seems to me, for the reasons that I've tried to show, it seems inevitable in some form in quantum mechanics. And there are many other things that point to the same thing. I would mention the PBR result as one of them, although I don't know how to make any, even after thinking about it. Joe and I thought about it a little. There's no way of making a direct connection. Petros and Joe and I thought about it. Petros Valden. Anyway, it seems at some level inevitable, but maybe these examples are unrealistically simple. That would be one way out. In the case of causal sets, or even in an expanding cosmos with some kind of cutoff on frequency, the nearest analog that you have a configuration space grows rapidly with time. This might well change things in an important way. Another thing is that quantum gravity, I would argue, is likely to be non-unitary. This will certainly have the potential to make preclusions less numerous, and you can compare this to collapse models in which something similar happens. Or if those cures don't happen of themselves, you have to try to moderate the inseparability. I don't think you can ever eliminate it, but change the scheme. The multiplicative scheme might not be the right one. Here's just a laundry list of possibilities. Maybe we should allow that certain precluded events do happen. Maybe we should try and get rid of some of this non-local relationships by considering co-events to be determined not globally, but to evolve with time. So that some of these, and I should say space-like separate things are in some sense at a later time if you slice space-time appropriately. So this may allow, moderate the degree of inseparability. It also points more towards a becoming as a versus black universe. Should they be relativized further, I'll skip that. But here I don't want to skip this last one, which is maybe there's some sort of statistical mechanics of coevents. In other words, maybe it's really true that the part of the world that you're thinking about does feel the effect of everything that you've ignored, but only in an average sort of way, which you can describe with a few parameters. After all, that's what happens when you describe a particle in contact with a heat path. Maybe there's something like that if we understood better the nature of these complicated systems. In that case, you'd be sort of asking for an effective field theory at the level of coevents. So to summarize what I'm saying, this kind of inseparability seems to me to be nearly inescapable in quantum mechanics. I discussed it mainly in this context of the multiplicative scheme, but the basic reason is interference and the possibility of destructive interference, as I tried to show. So the remaining question, or the question that this raises, is can we reconcile this inseparability with methods of analysis that we traditionally use in physics that assume we can isolate small portions of nature and study them without reference to the parts of nature that we've ignored. Whether or not this will involve notions of retrocausality specifically remain to be seen, but I think that evidence is accumulating that we need to come to terms with this kind of quantum inseparability before we can hope to describe nature in a truly realistic manner. Thanks.